First one, right? First speaker. Okay.
Wow, you're a wonderful crowd. Look at you. You're all ready to go. I want to be mindful of everyone's time, so I'm going to give it that extra minute for people to get settled.
Okay, on that. Let's go around that. Sure. Okay.
So welcome everyone to the 7th annual Farrukh Jamal Stanford ADRC Participant Appreciation Day. I'm Nusha Askari. I'm the Executive Director of the Center. And I want to first and foremost thank each and every one of you for being here with us today, for all your contributions, your dedication, your commitment to not only the study, the center, the field, but to helping hopefully one another and others and many generations to come with the contributions that you're all making. So on behalf of all of us, I want to give you all a big round of applause. So I'm going to just give you a few logistics, and then I will turn it over to Dr. Mike Gracious, who will do the introductions. First, I'd like to, on behalf of Dr. Victor Henderson, the director of the center, to welcome you and to thank you all for joining us. He's currently on sabbatical, but did want me to extend his well wishes and welcome to all of you. Secondly, some logistics. Restrooms, I think many of you now know, you can go through these double doors, and the two sets of double doors, it'll be off to your left a little bit. And to get back in, if you can't come in because the outer door does shut, you can come through that clear door that's propped open and come around this way through the outside. The other thing I wanted to share is all the speakers will have around 12 minutes to speak, and then we'll have around 12 minutes for QA. We will have a few people circulating in person, and then Lonja, who will be moderating the QA through the virtual. So the way we're going to do it is, as you think of questions, please, there are index cards and pens on your tables. Feel free to write them and raise your index card. And I'm going to ask each of them to wave to you so you know who they are. Nora, Hillary, where's Hillary? And Samantha. They will circulate and pick up the index cards. They will collate them. They'll try to find commonalities, and we'll try and be very, so we're doing it a little bit differently this year. We're going to try and just capture questions right after each speaker. I'll be the little bell ringer there to try and keep us on track with time as well. So I also then want to take the opportunity to thank all the people who were involved in coordinating the event. So I want to first and foremost thank my partner, Jamie Kramer. She's been amazing in helping me get this together. So thank you, Jamie. And at the registration table, we have Daisy Ma, Lonja. Thank you for, and Nora, Hillary, and Samantha again. Did I leave anybody else? Oh, and online we have Talisa. Talisa, wave to everybody. Say hello. And our friendly IT helper, Andrew. Thank you, Andrew. And of course, last but not least, all of our speakers, but we'll be thanking them individually as well. So without further ado, I'd like to turn this over to Dr. Gracious. Thank you.
Thank you, Nisha. All right. Well, what an incredible turnout. Thanks, everybody. I'll just second Nusha's thanks for showing up on a kind of strange weather day in such great numbers. It's wonderful to see everybody. I'm not Victor Henderson, as Nusha already pointed out. I'm Mike Gracious. In the next iteration, I'll be an associate director of the ADRC along with Beth Mormino, with Victor as the PI. Victor's on sabbatical. I want you to know he's not gallivanting around European capitals. He is in Europe, but he's actually in Aarhus in Denmark, where he's actually had a really strong relationship with that group there. Is an honorary professor at that university and does a lot of really important, I think, neuroepidemiological research with that group. The Scandinavians are very good at record keeping and other things, and so Victor's had a really good collaboration with that group. It's also they're currently I think just 8 hours of daylight now. So believe me, he's working hard. He wishes he were here. All right, so today's a day of gratitude, and you know, when thinking about how to open the talks today, it dawned on me, as it often does, you know, that these are tough disorders that we're dealing with: Alzheimer's, Parkinson's, Lewy body disease. They take a lot out of everybody, the patient, I think, first and foremost, the family, of course, even, you know, clinicians, researchers. It can be frustrating, it can be tough. And yet, I think we remain sort of optimistic and resilient in the face of setbacks along the way. And I, you know, in these sorts of settings, am sort of heartened by the words of William Faulkner. He's, you know, a Nobel laureate in 1950, shortly after the first use of the atomic bomb, and was kind of reflecting in his Nobel speech about how we not simply endure as humankind, but prevail in the face of these long odds, these kind of frightening setbacks. And so, you know, the question is, how do we prevail, right? And so, granted, this is not, you know, nuclear annihilation we're dealing with, but neurodegeneration has certain flavors that seem intractable and inevitable. And so, yeah, the question is, how do we do more than just endure through this? How do we prevail? And in Faulkner's comments, which I'd encourage you to read at some point, he touches on a number of human characteristics that I think will get us there, and whatever, you know, the obstacle is that you're looking to overcome. Part of that is endurance. I think we do have to endure through, you know, the sort of tough parts of these neurodegenerative diseases. There's no getting around that. In order to prevail, you must first endure. But then I think there are other attributes that will bring us further along as a community of patients and caregivers and researchers. And Faulkner touches on some of those. He talks a lot about compassion, which I think is really critical in prevailing. I would add generosity. I think that's a really big one, and sort of giving of yourself in whatever way that you can. And that, I think, is most beautifully reflected in this audience. And that's what I'm grateful for. And so I do think, you know, with that spirit of generosity and compassion and working together, we are going to do more than just endure, but actually prevail through these disorders. And you're going to see some very exciting and promising work from a very talented and more junior group of speakers this year. These are the rising stars in our ADRC that you're going to hear from. But so, you know, to sort of close on a note of gratitude to you, what is it that you guys have given? Well, you've, you know, literally given blood, I think sweat and tears. Metaphorically, yes, for sure. Any of you that have gone through the neuropsychological testing, which takes several hours, that, you know, I think entails a lot of sweat and occasionally tears even. Better than tears, you give spinal fluid, many of you. That's really the most precious resource that we ask of you in life. You've given skin biopsies, you've given your, you know, brains for brain scanning. And at the end of the road, and not before, you donate your brains, which is really an invaluable resource and moves the field along by leaps and bounds. So thank you again for all that you do and give. And I hope that you'll leave today with a couple things. One is some new, like I said, really inspiring information about Alzheimer's disease, Parkinson's disease, and Lewy body disease. And number two, and maybe as importantly or more importantly, some sense of satisfaction for having contributed to this effort yourselves. So thank you again. One more round of applause, I guess, for our participants. Yeah, and so with that, I think we'll dive into our talks. Pleased to introduce Kian Yunus. He's one of our junior faculty members here in the Division of Memory Disorders. Kian has expertise across numerous domains. He's going to speak to us today about clinical trials, but he's really interested in imaging and the lymphatic system. His K Award, which we're still waiting to hear about the funding levels, but truly a rising star, and I'm proud to turn it over to Kian.
I want to echo Nusha and Mike, really thank you for your wonderful presence, your wonderful contributions. I'm going to be talking a little bit about clinical trials. So I'm going to be kind of laying the land and maybe focusing on some of the more recent trials, maybe some innovation in the design or where trials will be going in the future. Just by way of introduction, Alzheimer's disease. Sorry, can you hear me okay? Oh, here. Oh, sorry. Let me actually. Yeah. Hello? Hello? All right, perfect. Thank you. All right. So Alzheimer's disease, it's a very complex disease. We think about it, we know it's defined by these two globs of proteins. They're very sticky and they're very hard to clear from the brain, amyloid and tau. Amyloid is outside the cells and tau is inside the cells. They eventually end up killing the neurons and affecting the synapses and the connections between brain cells. And eventually you see this atrophy or volume loss that is associated with symptoms and starting usually with memory problems, but could affect any cognitive domain. These amyloid and tau proteins we can look at we can study as biomarkers. So you could see them on CSF, you could see them on the amyloid and tau PET scans, and they basically start before the symptoms begin. So this is the conceptualization of Alzheimer's disease. It starts with biomarker change. Amyloid first in blue, in the CSF, so like in the fluid you see it first, followed by amyloid changes in the brain that you see on the PET scan, followed by tau in green, MRI changes, and then symptoms. So basically progression from normal mild cognitive impairment and dementia. There are more recent biomarkers, and this is very exciting. Thanks to you and people like you, there are now who donated a lot of blood. There are blood-based biomarkers. Highlighted in green are the ones that are FDA approved, and there are many more that could be approved soon. This is really making discovering this disease much faster and hopefully tracking with clinical trials, which actually led eventually to updating in the Alzheimer's disease diagnostic criteria. So there is a debate in the field which is actually trying to define Alzheimer's disease as a biomarker-based disease rather than a clinical disease. So a person could be cognitively normal but have Alzheimer's disease if they have the biomarkers like the amyloid or the tau. But amyloid and tau are not the full story. If you actually look under the hood, there are multiple hypotheses. There is an older cholinergic hypothesis. There is some glutamate toxicity. There is metabolism. There's a gut-brain hypothesis, insulin resistance, inflammation, glymphatic toxins. All these are subsumed under this cadro category, which kind of differentiates the mechanisms that could eventually lead to Alzheimer's disease. Cadro standing for Common Alzheimer's Disease Research Pathology. And this complex figure here basically tries to kind of lay the land for all the Alzheimer's disease clinical trials are currently enrolling in phase 1, 2, and 3. Phase 1 are the earliest trials done in healthy, normal individuals. Phase 2 are in Alzheimer's disease, but usually smaller studies, smaller numbers, and trying to establish efficacy and safety. And then phase 3 are the larger trials, and that is basically trying to establish efficacy predominantly and before FDA approval. So just kind of in a nutshell, some observations from this slide. There is 164 AD trials studying 127 drugs. There are 48 trials in phase 3, 90 trials in phase 2, 26 in phase 1. 76% are disease modifying. They're trying to change the biology of Alzheimer's disease. 12% cognitive enhancement, 13 neuropsychiatric behavioral symptoms, 4 prevention trials for people who have these biomarkers but still don't have any clinical symptoms. Current active trials require 51,000 participants, and 60% of these trials are industry funded. And then 77% of the repurposed medications, which are the medicines that are not created by pharma company, but all these supplements over the counter, vitamins, all these things are not funded by pharma because they're over the counter. So they're funded by non-industry sources. Just kind of zooming in a little bit, I'm going to highlight some of these medications in my talk. You could kind of look and scan and see your favorite supplement or favorite medication there. These are the disease-modifying medications. These are the disease-modifying small molecules. And, lecanemab or donanemab, these more recent Alzheimer's disease medications are also here studied in different ways. I'm not going to talk a lot about these medications. I think, again, thanks to you, there are lecanemab and donanemab, which are more, medications that are now currently FDA approved, although they're not for everyone. They have significant side effects, brain bleeding, brain swelling. We can talk about that maybe later. I want to focus on the ones that are now being studied. These are the cognitive enhancer medications and the neuropsychiatric and behavioral symptom medications. So going back to that Cadro kind of schema, there are 22% of these medications are targeting neurotransmitters, 20% targeting neuroinflammation, 18% amyloid beta processes. So you already see that targeting amyloid beta is not the most common mechanism that's being studied now. 12% synaptic plasticity and neuroprotection, 9% tau-related processes, 6% metabolism and bioenergetics, 4% ApoE, lipids and lipoprotein receptors. Again, there are some lower, 3%, some other mechanisms, proteases, and proteinopathy, growth factors, hormones, oxidative stress, neurogenesis, circadian rhythm, vascular factors, gut-brain axis, epigenetic regulation. So there are really amazing diversity in the pipeline. Now zooming on some of the mechanisms. So this is an editorial that we published about a year ago looking at the tau therapeutics. So now the current medications are approved, are attacking the amyloid, the lecanemab and donanemab. But amyloid is not the most important protein. It's only part of the story. Tau usually correlates better with what symptoms. So these are the tau medications. Highlighted in red are the ones that are still active, and the one below that are the ones that failed, basically. So older trials targeting tau have failed for different reasons. Tau is a very large protein, and they were only targeting one of the ends, the N-terminus, which is not as relevant. The antibodies that they were using were IgG4, not as relevant as IgG1s. So more recent trials are actually targeting the mid-region of the tau and using more effective antibodies. So in the clinical trial of Alzheimer's disease conference, which was just 2 weeks ago, I'm going to be highlighting some of these findings. So there's the Together trial, the bepranemab, which is an anti-tau that is targeting the mid-region of the protein. And they basically showed that this medication lowered tau on PET scans. So in black, you see the placebo, and then there are 2 different doses in blue and a higher dose in red. And then this is on the y-axis is basically the amount of tau reduction in the brain. So they did actually successfully reduce the tau in the brain, but this is not enough. We want to see difference in clinical symptoms. And this was a phase 2 study, so the sample size is small. And this really here shows that they did not meet their primary endpoint. So there were no differences on the clinical dementia rating scale, which is a scale that measures function in like memory, orientation, judgment, things like that. However, they did show improvement in cognition. So people's memory seems to have improved a bit on the ADAS-Cog. And then they actually, in their design, they had planned subgroup analyses and gated statistics where they were able to do some comparisons with enough power, and they showed that people with lower tau may benefit more than people with high tau, and people with ApoE4, which is a gene that informs risk for Alzheimer's disease, had less benefit. Another trial that actually this is a phase 2 as well, that was published last year, and the phase 3 stopped recruiting now, so they're basically just hopefully we're gonna hear the phase 3. Again, this is an antisense oligonucleotide, so it's that kind of changes the messenger mRNA of the tau gene. And then again, in black, you see the placebo, and then you see that also this cleared tau protein. Here, these are the brains basically of people who got the medication. Red indicates the tau, and then you see over time, there's less tau. They also showed really encouraging cognitive findings. So I'm excited about this, and this is actually an intrathecal study. So the medication, this genetic medication, was injected in the back, and then I think it's one of these kind of easier access to the brain. One very interesting how the future of the field hopefully is going to be is platform trials. So it's not going to be one medication, but a person would sign up for a set of medications, and then depending on where they are in their amyloid and tau and potentially anti-inflammation, so you could add multiple medications depending on where people are in their disease and how they respond. This has proven to be effective in cancer therapy. There are also prevention trials, so giving these medications to people who are biomarker positive but still don't have disease, and this might prevent the disease from happening. We're waiting for the result of one of these trials very, very soon. It ran for about 4 years, and this year they actually have the results, but they haven't shared. They share in this conference. They shared their biomarker data, but they didn't share their clinical outcomes. So really looking forward to that. This is one of our trials, brainchild of Dr. Mike Greich's. It's looking at a medication called bumetanide, which is a diuretic, a loop diuretic, potent diuretic. That in a very interesting study that was data driven, they looked at 13,000 medication that is already approved by the FDA, and looked for which one will change the transcriptomic signature, the gene expression or the proteins in the cells from disease-like, from ApoE44 AD to healthy-like. So in the upper bar code, basically the red shows genes that are upregulated, and then blue genes are downregulated. And then the lower one, after we give them bumetanide, you basically flip that. Also in cancer therapy, that's shown to be a positive, helpful technique. Then they went back and did this in mouse models, and there was some improvement in cognition, as well as reduction in amyloid protein. So you see here all these kind of brown. This is amyloid in the mice, and then there's less amyloid when exposed to bumetanide. Also at UCSF, Mount Sinai, and Stanford, we looked at the health record of people who were, so the medical health records for people who were exposed to bumetanide, and found that in these 3 cohorts, people who got exposed to bumetanide were less likely to develop Alzheimer's disease. So we actually now have a trial that is recruiting people who are interested to investigate this medication. These are the two other trials that we currently have. The START trial, which is looking at a smart molecule that changes receptor called sigma 2, prevents the amyloid from attaching to its receptor. Another trial is ARIBIO trial, which is looking for a vasodilator to see if it helps with the with cognition. Some other trials from the CTAD conference. This is a combination medication that used intranasal insulin with another medication called IMPA that's used in diabetes. So sometimes people call Alzheimer's disease diabetes like 3, basically type 3, because there's insulin resistance in the brain. And here, giving this medication, they showed that they improved cognition. So again, small study. They improved the white matter health in the brain, and they reduced tau. And then just an example of how precision trials can work. They looked at the profiles of inflammation in the blood, the thousands of proteins, and they found specific inflammation markers that they were able to target and improve. This is a trial that looked at transcranial magnetic stimulation and showed some efficacy and target engagement. In red are people who got TMS, and they basically did not get worse compared to people who didn't. And then just kind of a closing point, these are very heterogeneous. Each person has their own fingerprint and different percentages of different pathologies. So Alzheimer's disease has 2 proteins, but then many Alzheimer's disease patients have Lewy body disease. They have vascular disease. So we have to adjust and make sure that we're addressing each one of these co-pathologies. In closing, I think we still need many more treatments. One comment: we need more representation of underserved communities. And it's really exciting to look at the pipeline and see what will pan out. This is our clinical trial team information, and feel free to reach out with scanning the barcode or emailing the emails there, or talking to Lanja back there. And thank you so much for listening.
Questions, please write them on the index cards and And then what we'll do is we'll alternate one in person, one virtual. Lisa, let me know if you have anything virtual. Lisa, do you want to start with the first one while we're gathering the in-person ones?
Hello, sorry, I was just helping someone get into the meeting. So one participant was asking if there's any way that we can kind of recruit based on findings from biomarkers we collect, and if there's any way we'll be able to reach out to them that way.
It depends on the trial. I think I mean, usually, so I definitely think the answer is yes. So if you have biomarkers, you could definitely use that information, but most likely the kind of trial would want to repeat some of that. But it's already a good information to have that I guess that makes definitely things faster.
Okay, great. And I can also add too, just on my own, I know usually on our quarterly newsletter, we do like to try and let you know what others, so feel free to just kind of look at the last page of the newsletter if you'd like more information on the other studies that we're collaborating with.
I'll start off. Okay. Oh,
Okay.
okay.
Do you know what the proposed mechanism of action is for the AR 1001 trial?
Is that the not really, no. We can look it up. I mean, yeah. I'm not sure which trial is that. It's hard to keep track of the like letters and new numbers.
Combine the two.
So, oh, Aribio, yeah. Oh, sorry, thank you. Yeah, so it's actually it's an erectile dysfunction medication. Basically, that's it's like an NO inhibitor that kind of vasodilates the vessels. So similar to I think this is an old hypothesis, and it's been tried before to kind of vasodilate the vessels and maybe get more perfusion, more blood to the brain. It's a promising and hopefully safe. There's been similar trials done before with not great outcomes, but this is a new mechanism, or kind of a change in an older mechanism.
All right. Well.
Sorry for alternating between online and. So, Dr. Yusuf, did you say that specific diabetics are showing promise? Can you elaborate a little bit, please?
And medications that are targeting diabetes, they don't only affect diabetes, but they affect metabolism in general. So you could imagine that improving metabolism, insulin resistance could help the brain, help its resilience. So that phase 2, there is actually 2 studies now that I know of that are targeting, they're using insulin or like diabetes medications. Another one is using metformin, and the basic science data is really interesting. So the preliminary data is really promising. Sugar resistance. It seems like can be a very promising. We still have to, all these trials need to kind of wait for the final results. It's really kind of dangerous to try make conclusions based on mouse models and cell cultures and things like that. And that's why we need larger trials. So the fact that they're promising, doesn't mean that we can recommend them yet.
Okay, we have 2 trial questions here. So the first one is, can a person currently enrolled in a trial participate in another trial? And then the next question is, how many subjects are in the trial right now?
Depends on people can't be on 2 different clinical trials, basically interventional trials. So if you're giving a medication, most protocols will say you can't take you can't be on another protocol. But if you mean by a trial, like a study, like an observational study, then I think it's possible. You want to kind of discuss it with a clinical trial team. It's like a individual by individual basis. Yeah, and then there was another piece.
Yeah.
I'm not sure what trial you're referring to.
The question did not say specific one, so yeah.
Oh, we have a large clinical trial program, and trials open up and close kind of fast. So usually these are like international trials. You recruit like 5 patients in a site or so. Yeah, but then yeah.
Okay. Okay. We have a question regarding FDA phase 3 clinical trials. And question is, does the FDA require a phase 3 clinical trial like for drug approval? And what is required for a trial to be considered phase 3?
Thank you. That's a great question. So yes, the FDA requires at least one FDA approved positive trial, and sometimes 2. In the majority of the cases, they require 2 trials. And the main outcome that they are looking for is clinical benefit, so cognitive and functional benefit. So showing change on biomarkers, not really important enough unless we see benefit, like a change in the cognition of people and their functional performance.
Mm-hmm. Thank you.
Yeah.
I have a good one. Are there any trials taking people who are amyloid positive but asymptomatic for Alzheimer's disease?
Yes, that's a great question. There is one that closed recruitment recently. That's the one I just mentioned. It's called the A345 or AHEAD study. They actually we're gonna hear the results from it very soon. There is another one that's using a different mechanism that's currently enrolling, but we don't have that trial yet in our center. So there are also all the exercise trials and healthy lifestyle modifications. So yes, there are. I think the main one is the AHEAD trial. Hopefully they're gonna give us results this year.
We have a question regarding the MRI PET scans that are part of our clinical trials, and someone's asking, do they look at amyloid only for these MRI PET scans?
And here in our center, they look at they do two scans. One is amyloid PET, and the other is tau PET, and they both have an MRI with them. So the first one is amyloid, the second one is tau. So you basically won't have the tau unless you got the amyloid scan.
Thank you. Okay, we have one question to close out the session. What drug class are you most excited about?
You met. I think the anti-tau trials are the ones. The second wave of these medications are really what I'm looking forward to hear about. Yeah. All right. Thank you.
Hello. There we go. Hi. All right. That was great. Thanks, Kian. Excellent questions. Keep them coming. So our next speaker is Carla Abdelnour. She's an MD PhD. She comes to us by way of Venezuela, initially for medical training, and then did her neurology training in Spain. We've had her here for, 4 years. 2 years. It feels like 4 because she's done so much work, not because and we're trying desperately to keep her, and she's working on a training grant so that she can stay and keep doing this great work. So Carla's gonna, her particular expertise is in Parkinson's disease and Lewy body disease, dementias, but obviously also the overlap with Alzheimer's disease. And she's gonna take us through a whirlwind tour of thinking about how these different protein markers can distinguish Alzheimer's from Lewy body, and also I think maybe talk about cases where we see pathology, both types of pathology in the same patients. So Carla.
Hello. Well, thank you very much for the introduction. I wanted to start today talking about a cognitive function that sometimes we don't talk about frequently. So we're talking about neurodegenerative diseases. Mainly they affect memory. And I think we're all pretty much know about memory, language, or attention. But there is another cognitive function called social cognition. And social cognition is our ability to understand the emotion of others, understand their motivation. We are also able to have empathy because of this function. We can put ourselves in the shoes of others. And we can, and I think I'm always amazed about this function because our brain have structures, we have neurons that have evolved to be able to live in a society. And I think that is amazing because we are not isolated entities. We need to live in a community, actually, and our survival depends on our ability to live in that community. And I think social cognition is the function that helps us to tackle very complex problems, like the complex problems that we're trying to tackle here. We're trying to look solutions for very difficult diseases to treat, neurodegenerative diseases, and this is very complex. So I think social cognition is a very good tool to find solutions. And today what I'm going to talk about is how we're putting our brains together to find markers that help us to identify better our patients in the clinic. So Kian talked about a little bit already about Alzheimer's disease, and he explained that Alzheimer's disease, when we see brains in the microscope, we see accumulations or deposits of a protein called amyloid beta outside the cell, outside the neuron, but also inside the neuron, there are deposits of a protein called phosphorylated tau. There is another disease that I'm very fond of that is called Lewy body disease, and is characterized by the deposits of another protein called alpha-synuclein. And alpha-synuclein is clumped in these round structures inside the neuron called Lewy bodies. And Lewy body disease clinically is composed by two diseases, Parkinson's disease and dementia with Lewy bodies. So this is the way that we usually classify the diseases. But what happens in reality, as Kian also mentioned previously, is that these diseases often coexist, and there is a lot of patients that have both diseases in the brain. And we know that cases that have both pathologies have worse prognosis, and also we think that they might have a different response to treatment. So what happens is that we have seen in basic science studies that some neurons can harbor both tau and alpha-synuclein, and we think that this may lead to a faster neurodegeneration, but is also amyloid present. Now the question is, how do we detect these abnormal proteins in a person? Because the issue is that with the brain, we actually don't want to take a biopsy of the brain, right? To be able to see these proteins. Well, we have come up with biomarkers. These are indirect measures that we use that tell us if these proteins are abnormally present in the brain or not. And today I'm going to talk about
Hi, everyone. I'm not sure if we're in the big meeting, but I will email or text Nusha.
Sorry, everyone, just bear with us.
Here we go. Okay. Great. So we were saying that we are able to identify different proteins in the brain. The last one that I was talking about is one that has to do with inflammation, but there is another one that has to do with neurodegeneration that is called neurofilament light. What we don't have in the brain, in the blood yet, is a biomarker for alpha-synuclein, but we are hoping to have that available soon, hopefully in a couple of years. We're working very hard to track that protein also in blood. So in the study that we conducted with the Stanford ADRC participants, Ted from the ADRC biomarker core analyzed the plasma samples, and we studied the plasma phosphorylated tau 181. We have studied that biomarker in people that have the clinical diagnosis of Alzheimer's disease, but we're interested in our lab, the Boston lab, to study this biomarker in people with Lewy body disease, so in people that have Parkinson or dementia with Lewy bodies, because we know that some of them can have also features of Alzheimer's disease. So that's what we did in our study. We analyzed this biomarker in these sets of participants, and our study showed that this biomarker is very useful to identify Alzheimer's disease co-pathology or concomitant Alzheimer's disease in Lewy body disease patients. And also, we think that this biomarker can help us to see what patients might have a worse prognosis, because our studies show that people that have elevated levels of plasma beta 181 at the time of the blood collection, they had worse performance in global cognition. But also we were able to see that higher levels of this biomarker predicted the patients that were going to have a faster decline in functional impairment. And also we saw that rapid increases in this biomarker led us to predict the people that were going to have a faster decline in memory and functional impairment. So it seems like this biomarker not only works very good in Alzheimer's disease, but also works in Lewy body disease, and we can use it to diagnose the presence of concomitant Alzheimer's disease. We can use it to for prognosis and for monitoring of our patients. So we hope that in the future, we can validate these results in other similar cohorts. And if these results replicate, we could use this biomarker in clinical trials or in clinical settings where we are able to use it with our patients. That's the goal. Now, another biomarkers that we're studying are in the cerebrospinal fluid. In the cerebrospinal fluid, it's an amazing biofluid because it's in direct contact with the brain. Also, the good things about biofluids is that we can study thousands of proteins at the same time. So it gives us a lot of information. And the way that we obtain the cerebrospinal fluid is with a procedure called lumbar puncture. So this is a very standard and safe procedure that we do in neurology. The cerebrospinal fluid is a liquid that is in the cavities of the brain and also surrounding the spinal cord. And what we do is we do a puncture in the lumbar space between two vertebrae, and we take this liquid that is transparent as water. And there we are able to identify 3 proteins now with very high accuracy. So we're able to identify amyloid beta, phosphorylated tau, and alpha-synuclein, which we're interested in studying these mixed cases. And what we are doing right now is using that information from people that have donated their CSF in our ADRC to classify our participants in 4 groups. So we have people that have normal biomarkers, a group that we call quote unquote pure AD, a mixed group with AD and Lewy body disease, and a pure group with Lewy body disease only. And in collaboration with the Alzheimer's disease biomarker core and also colleagues from Gothenburg in Sweden and colleagues from Spain, we're analyzing several plasma biomarkers because what we want to do is see if we can use them in isolation or in combination to diagnose better our patients. So I don't have results today for this study because we're currently doing the analysis, but we're very excited to be able to combine different biomarkers for a better diagnosis. Because at the end, what we want to have is accurate and early diagnosis of these diseases. And here, I'm putting the patients in the center because the patients are in the center of all our actions. And I want also to remind you that sometimes we forget something that is very clear for all of us here at the ADRC, that people living with the condition are the experts. So we are working together in this research endeavor to fight dementia because science is a team sport and you are also part of our research team. So all of the things that we're showing you today as results of our study are actually because you're part of our team, and we are very thankful for that. So if you have any questions, I'm very happy to answer any question. Thank you.
Okay. In the butanamide study, phase 2, doing is the butanamide study doing biomarkers with blood draws?
Whoa, that's a very good question. So I used to do, yes. So Kian is telling me that yes, because I used to do a lot of biomarker clinical trials, but I haven't been keeping up with that literature that much. But Kian says that yes, that they're using it. Thanks.
So Lisa, there's a question online. Do you want to ask that?
Yes, this question is asking, what if the doctor cannot get any spinal fluid during the exam?
That's a very good question. So there are a few cases, it's true, where sometimes the procedure is a little bit difficult and we are not able to obtain the biofluid. So if the biofluid is for a diagnostic purpose, there are different ways that that can be done. So I mean, if that procedure needs to be is an infection, for example. So the diagnosis for that is with a lumbar puncture. So you do that. You will have to try to do that. So in those cases, you will try to do the procedure in another time. And there are different methods. So sometimes we can guide the lumbar puncture with radiology to be able to obtain the fluid. Now, if that lumbar puncture is for research and we can't do it because it's difficult, we're not going to put that person through all of that just for the research purposes, right? So I think it depends on the person. If this is something for diagnostic purposes and that's the only option, we are going to try to do it again. But if it's for research and if we're not able to obtain the fluid, that's okay.
Great. I have a question now in regards to phosphorylated tau 181. Certainly. Is plasma phosphorylated tau 181 linearly related to tau signal in brain PET and or CSF?
Whoa, that's such a good question because actually we're still trying to understand that plasma phosphorylated tau 181 is associated with amyloid burden in the brain. So it doesn't seem to be associated that much with tau in the brain. And we don't clearly understand why, because being an isoform that is in the tau protein, it should be associated with tau. So we're thinking that that might be because when amyloid plaque starts to form, they also might interfere with tau metabolism. So maybe there is soluble tau present that we're picking up in the blood. So that's one hypothesis that we have. But also we have to be mindful that blood is in the periphery, and in the periphery, so not in the central nervous system, there might be other processes going on that we need to understand. So we don't know if we're picking up something in the periphery that has to do with the amyloidosis that is happening in the brain, because these associations and these studies that we do are statistical associations. So we are not able to draw causality from those results, right? But yeah, that's a very good question. It's more associated with amyloid than with tau.
All right, we have another good one here. Have you ever seen high alpha synuclein without Lewy body disease?
So so that means that if we see, yeah. So in the CSF, if the question is if when we identify abnormalities in the CSF, if those cases always have Lewy body disease, it seems like the answer is yes, because there is a very recent study analyzing CSF with brain tissue. So that's the gold standard for all of these diagnoses. And everybody that had Lewy bodies in the neocortex had a positive cerebrospinal fluid for alpha-synuclein. Now, it's true that people that have Lewy bodies, maybe not all of them develop the diseases. This is something similar that happens with amyloid. Not everybody that has amyloid in the brain will develop the disease at the end, and we don't understand why. Now, Lewy bodies, I think, and this is probably a personal opinion, are kind of worse because when they are present, most likely the person will develop the disease. So, and people often they live a shorter period of time. So I think there must be something that is worse in the case of this proteinopathy of these Lewy bodies. But I think we need more studies to understand that.
And we also have a question on Zoom asking if you can explain a little bit about tau, what it is, what it does.
Whoa. Okay. So all these proteins, they're such a very good questions. You're definitely part of the research teams, because you know what? Sometimes those questions is like, yeah, I have to think about that and put it in my paper. So the tau is a protein that is in the structure of the neuron, and that structure is what we call the microtubules. So the neuron have structures that are along the axon that help the communication and build their own body. So the tau protein is present in the body, in the microtubules of the neuron.
Okay, I have a question. Is the blood drawn from ADRC subjects when they come in for their clinical tests? Do they test for the new blood biomarkers?
Yeah, so we're testing for a lot of these biomarkers. We're analyzing them for research purposes. And Ted is going to talk about one of those, beta 42, beta 40. We're analyzing 181. And I think we have available other biomarkers for research. And we are also collaborating with other laboratories to analyze. So we're able to analyze in biofluids, as I mentioned, thousands of proteins. So with another method that is called proteomics, for example, we can identify thousands of proteins. So yeah, we're analyzing the new ones and probably trying to find new ones also in the future to discover more biomarkers.
Great. And one last question from us is, can you detect alpha-synuclein in CSF but not plasma? Why?
Yeah, we don't know. This is very difficult. So the issue is that the levels of alpha-synuclein in blood are so low that we're not able to detect it in plasma. And the other problem that we have with blood is the alpha-synuclein is a protein that is also present in the erythrocytes and is highly present there. So when we're trying to identify that protein in blood, we have to make sure that we're not picking up any alpha-synuclein that come from erythrocytes for a red blood cell. So that's I think those are the main problems. The very, very, very low concentration, and we're still don't have the technology to identify those very low concentrations of this protein. It's the contamination that can be present because of the red blood cells.
Thank you.
That was amazing. One quick off the cuff comment about biomarkers in general. So, well, 2 points, I guess. One is these hit the scene around 2009, 2010, especially with amyloid PET as a biomarker. And we discovered to our horror and shock that when you applied these to people that were being enrolled in Alzheimer's disease studies, when they first came out, people were being diagnosed clinically and enrolled in studies. And we found out that 25% of people enrolled in these studies didn't have the biomarkers for Alzheimer's, meaning they didn't have Alzheimer's disease. They had something that looked like Alzheimer's, but it wasn't Alzheimer's. You can imagine if you're trying to get a drug, approved and show that it works, if only 75% of the people in your trial have the disease, it's going to be a tough task. So they've been incredible. The move from, spinal fluid to imaging to now plasma is really encouraging. It makes them much more widely available, much easier to do, to follow longitudinally, as Carla mentioned. But I don't want people to forget about the importance of spinal fluid, even though we can answer a lot with plasma now. And as you'll see from our next talk, even with digital biomarkers, there's really no substitute for spinal fluid. So please keep giving it or consider it if you haven't already. All right. With that, let me introduce our next speaker. So Dr. Ehsan Adeli is a junior faculty member here in psychiatry. He did his PhD in computer science at Carnegie Mellon University in Pittsburgh, and is an expert in the use of artificial intelligence, machine learning, as applied to digital biomarkers in Alzheimer's and related disorders. So, Dr. Adeli. Probably use that.
Awesome. Perfect. Yes, thank you. First, I wanted to thank everybody here because of your amazing contribution to science and all of our research and everything. And okay, closer. Yes. Yeah. So yes, after hearing about disease mechanisms and biomarkers and the breakthroughs in medications over the past years, I want to talk a little bit about some other approaches for understanding the disease, generally Alzheimer's disease, cognitive impairment, mild cognitive impairment, and so on, through digital devices. And I will be talking about using an automated physical performance battery as a digital marker for Alzheimer's disease and mild cognitive impairment. So we know that movement disturbances are known to be among the earliest manifestations of cognitive decline. What we are doing is we're building a tool, a mobile app of gait and postural control assessment based on an extended version of the short physical performance battery test, or SPB for short, using artificial intelligence and computer vision technologies. Our tool, as you can see here, first video records the test, the individual performing the test, and conducts autonomous motion tracking and unlocks a new range of digital measures beyond just clinical scores that are used. As you heard a lot about the medications in Kian's talk, with the recent breakthroughs in disease-modifying drugs for Alzheimer's disease, there is a growing need for cost-effective, scalable, and easily administrable screening tools. And among the key early manifestations of neurodegeneration are changes in motor function, such as gait and postural control. Recent advances in 3D human understanding has made it possible to accurately model human movements. We have developed several robust technologies to accurately reconstruct and understand human movements in 3D. This is just a video, an iPad video of the individual. Not sure why the video stopped. Please. Anyways, that's a video. This video is working, this one is not. So the individual is walking towards the camera and back, and this is an iPad video. We were able to reconstruct all of the movements in the 3D space, and then you can see the side view of the person moving, showing that we were able to actually create this 3D movement of the individual completely. And on the right, you see detailed movement measures that are captured by just an iPad video example. For example, knee angle over time, left and right knee, foot contact with the ground, left and right foot, and even toe base. And with that, we were able to get detailed analysis of walking sequences. We can extract all relevant information of the walking cycle, including walking time, gait speed or walking speed, double support time, average dorsal inclination angle, and many others. So to test this technology, we first ran a smaller study to automatically estimate the gait impairment scores. This is myself simulating a gait impairment, gait disturbance, walking in a straight line. So the 3D human skeleton data was extracted only from the video itself, which basically reduced the dimensionality of the data, was really efficient in the number of samples because it's a low dimensional data. And it also anonymizes the data because that's what we analyze, and we throw the videos away. And then only this skeleton was used to estimate gait impairment scores, which could be measured either by MDS UPDRS exams. Some of you may be familiar with that because you've gone under that test, and also the SPV test that I just introduced. And so, as I showed, this test is going to be a way of extracting or estimating the gait impairment scores. We use data from Stanford ADRC as well as some other sources of data at the Stanford, and we worked with our expert neurologists within ADRC to rate the gait impairment scores, a number between 0 and 3, basically 0 being normal and 3 severe sign of gait impairment and postural instability. And using the data from 3 neurologists, we were able to create a system, a model that was accurate at least 87% of the time, at least with one of the raters in our data set. What we did was to understand what the model has learned, because I'm sure one of the questions that I'm going to be receiving is around AI, trustworthiness of AI, and if we can explain what it did. So to understand what the model learned, let's look at these visualizations of samples from our data with 4 gait impairment scores. As you can see here, the dark lines are the current skeleton of the individual, and the fading lines are basically their movement over time. So this is a summary of the subject's movement, the individual's movement. And you can see left and right are also separated by blue and red. As you can see here, normal walking has a free movement style, while in scores 0 to 2, 1 to 2, you do see reduced arm swing and range of pedal motion. And in score 3, you also see some levels of instability, loss of control while moving, and so on. We also looked at the velocity and the movements of different joints in the body, and these are the top 4 joints that their movements contributed a lot in being able to detect or estimate the impairment scores. So with this technology that we've built and what we've published as part of a project that we've run within Stanford ADRC, we started looking at the short physical performance battery, which includes 5 different parts. The first one is a balance test and includes side-by-side stand, semi-tandem stand, and tandem stand. And the second one, basically the fourth one, the second major test is the gait speed test, and finally 5 chair stance tests that characterize the SPV battery, the short physical performance battery test. We collected data within Stanford ADRC of 112 participants, which was enough to run the preliminary study of identifying if gait and gait impairment are related to mild cognitive impairment or Alzheimer's disease compared to healthy control data. We did observe some correlation between the MoCA scores, basically negative correlation with MoCA scores and gait test time. MoCA is one of the cognitive tests that here what we see is as MoCA increases, the time required to complete the gait test decreases, as also you can see within this plot. This was a good start, but then one of the interesting things that we observed was in the repeated chair stand test scores. Here we see the box plots between the healthy individuals and MCI and Alzheimer's disease individuals, and the distribution of the scores and everything is shown here. What we observed here was there was a significant difference between the scores, the repeated chair stand scores between healthy and MCI and Alzheimer's disease individuals. Similar type of behavior was observed in the single leg stance test, a decreasing behavior from healthy to MCI and then Alzheimer's disease. This plot showed the same type of pattern in which this scatter plot with the MoCA score versus single leg stance test shows as and a slight positive linear correlation, a correlation between the 2 variables, MoCA and chair stance test, which was all very indicative of using this type of test and the technology for developing digital biomarkers. So we were able to see what movement features are differentiating factors across different gait scores. So for different gait scores, we looked at movements of the body and we evaluated movement variability, velocity, and angles across 3 different dimensions, all 3 dimensions of X, Y, Z. And you can see the statistically significant variables here listed. So with that, movements of these joints that are detectable by processing the videos can serve as very good digital biomarkers for gait impairment severity in neurodegenerative diseases. And to conclude, I must say that this algorithm paired with identifiable digital biomarkers is scalable and can be deployed on any device, including a mobile device. It can generate repeatable measures and can help track the disease progression or even recovery over time. When tracked over time, the trajectory of changes in the digital biomarker can identify an early indication of anomaly and potentially the start of cognitive decline. At the end, again, thank you. This project was part of Stanford ADRC as in the REC component in its research education component. And after that period passed, we extended the work into understanding the neural mechanisms of gait and gait impairment, which is part of this R01 large study, R01 recently awarded for understanding the science behind gait and gait impairment and neural mechanisms. At the same time, this project was funded through Mass AI and Technology Center, which is also a National Institute of Aging center and they funded the development of the mobile app. And that's how we are building the app right now. I also want to thank all of my amazing collaborators, my postdoc, and the students that I presented their works here. Thank you, and happy to take any questions.
I don't know. Well, I just wanted to comment, this is a great example of how a research education component can have some amazing, outstanding investigators come out of it. So thank you, the Ehsan, and I'm so glad to see that there's been wonderful progress that's moving you further forward in your trajectory. Congratulations.
Thank you.
All right, to start off the questions, we have, our gait, posture, and balance impairment different between Alzheimer's disease, Parkinson's, or Lewy body disease?
So that's a great question. What we observed within the data in the data that we had from Stanford ADRC, we observed significant differences between healthy individuals, same age range, and individuals with MCI and Alzheimer's disease. Right now, we are running a similar study to compare the MCI individuals, which is part of the R01, MCI individuals with Alzheimer's disease pathologies versus MCI individuals with Parkinson's disease pathologies. With Lewy body, we had, unfortunately, much less data to create it. We didn't have the power to create that statistical significant differences and so on. So that's an ongoing research.
We have a question about your avatars. One of your avatars showed extension of the fingers while walking. Is that a measure you looked at?
That's a great question. The short answer, actually, there is no short answer. So it's yes and no. The no part of it is because it's not one of the measures that we extracted to see if there is any explainability of the models and so on. But the part that is yes, it's because we built a model that only looked at the skeletons, the entire skeletons, without any summarization of like any parts of it or any joints. So if there is any extension of the hand area, the feet, then we capture that part, we put it in the model, but we didn't look at the piece that is it explainable, that part. The thing is that so basically the AI model is looking on that and can make a decision based on that. That is yes, but we didn't really, because that reconstruction of fine movements is not really reliable yet, and it's not very robust. in terms of being accurate, we didn't read too much into these components. So I hope this answered the question.
Is this software being adopted by clinicians elsewhere?
Elsewhere. Okay. Here, yes. But elsewhere, we are. So in order to roll the software out and as a mobile, I mean, it's a research tool right now. So we are collaborating with individuals, with other ADRCs in other parts of the United States. We have collaborators on this very project with, I showed Massachusetts, in Boston, also Boston University, UCSF, and other ADRCs within United States. But right now, it's mostly in the research stage and research data collection and evaluation stages. So no, it's not being used regularly, but it's being used for data collection and evaluation of the digital biomarkers that we talked about.
Okay, I have one more. So in synucleinopathies, we see multiple prodromal indicators like sleep disturbances and autonomic system failure. Can you address how mobile digital monitoring might apply in these?
So that's a great question. So about the sleep and other type of markers, we're going to hear in the next talk. So I'm not going to go into those. But one of the aspects of these types of technologies, and especially looking at movement and motor markers, is that they could be captured also passively, not just actively within the tests that are happening in the ADRCs or in clinics. First, if you have this mobile app, it could be used by any individual at homes. So that's one thing. The other thing is that an extension of this work that we are exploring right now is, instead of using the active participation in the test and then being filmed on a mobile device, we are looking into capturing movement patterns that could relate to behaviors that we could call them neuropsychiatric symptoms, and those neuropsychiatric symptoms are basically also very early indicators of some neurodegeneration. So I think the answer to that question was definitely relevant, yes, and this is the technology that could be capturing other factors passively.
Okay. We have a question about other variables that you're studying that you have digital data sets for example, things that corroborate with diet or social network use or buying behavior even. Are there any correlations there?
So this is a great question. Yes, many of the earlier research that was done in identifying digital biomarkers was, yes, exactly using these types of social network engagement or mobile device usages, or even some sensors that are attached to the body, so sensory data. So all of these are still being studied. There are many ongoing projects within Stanford I'm aware of or I'm part of that we are studying new sensory data to quantify relations with cognitive impairment and so on. So all of those are quite relevant. Like, for example, one of the very promising ones is speech and markers that we can extract by through speech. Again, another amazing project at Stanford ADRC. And so, yes, I think all of these could be studied. But in terms of one of the things that I probably want to allude to is the sensitivity and specificity of these biomarkers. The biomarkers that we studied, we saw Carla and Kian explain, and you'll be hearing more about them, are much more specific and sensitive to the disease itself Digital biomarkers, on the other hand, are probably sensitive, but they're not as specific to the individual disease. And because of that, they are very good for early stages, rolling out some of the diseases, and basically minimizing the costs, the follow-up costs that are required for running all of the tests that you have to go under if you're to be diagnosed with any of these diseases.
Okay. So we've talked about a lot of different aspects of Alzheimer's disease so far. But what's like the first thing that shows up when there may be a diagnosis of Alzheimer's disease?
Ooh, that's that's a very hard question. So two things. First, since I'm a computational neuroscientist and not a Alzheimer's disease scientist or neurologist, I'm not the most qualified person to answer this question. That's the first thing. The second, I think, the second note that I wanted to mention, I think there are a wide variety of signs and symptoms that you're going to hear more about them today, but gait and mobility impairments have shown to be of the earlier signs, if not the earliest. So let's leave it at that.
So I think that is our last question. Thanks, Dr. Adeli. That was great. Very exciting, very encouraging. Yeah, Anusha asked me to weigh in on that last one, which is a tough one. I mean, I think symptomatically, as many of you probably know, probably 70% of the time, the first problem that either the patient or somebody close to them, their spouse or adult children, will notice is memory trouble, typically repeating the same question a few times over the course of a day, misplacing things more than they used to, and doing all those things more than other people their age, right? Because we all forget where we left our glasses. Everybody has 5 pairs of glasses around the house. That's probably normal. But, you know, if you're misplacing your car and you need to drive around with the security guard in the parking lot, you know, it's a little further afield. Those are worrisome. So most of the time it's, you know, some sort of early short-term memory issue. About 30% of the time or so, it's something other than memory. So there are different sort of flavors of Alzheimer's disease clinically, and the sort of two common ones that we see are either language variant of Alzheimer's. So people start with lots of word finding trouble. Their memory is actually normal for the first several years through this, but their language starts to deteriorate. So that's the language variant of Alzheimer's. And then the second sort of, you know, the memory version or the amnestic version is most common. There's a language version kind of equal with the language version, but less common than memory, is the visual spatial version of Alzheimer's disease. So people have trouble with visual spatial skills, parallel parking, finding things that are right in front of them, guiding their limbs to targets in space. Very different feeling picture than the typical memory version of Alzheimer's. But those are less common. So 7% is memory, and then maybe 15% language, 15% visual spatial presentation. All right, with that, you want to take it over, Nusha?
Yes, thank you. So can we all join together to thank our first round of speakers? Thank you all so much. I think we've had a little bit of a hiccup with our coffee refreshment, but there's still some coffee and other refreshments. We have about 10 minutes for break. Feel free to get up and stretch your limbs. There should be, hopefully, this is the last call for refreshments. They'll be coming in about a half an hour to clean up, and I think that's probably what they're counting on. So sorry for that little hiccup, but thank you all so much. And when you stand up, get up and go deep breath. And release it. Yeah. I always lead you in these exercises, don't I? So let's do it. Inhale. Exhale. Inhale. Exhale. And one more. Inhale big. And stretch your arms back. And exhale down. Feet. 1, 2, 3. You're set.
Oh yeah,
It's up? Okay.
and people have been using this.
Yes, that's for advancing.
Great.
Thanks.
Okay, we're getting ready to start again.
Okay. Hopefully you got the last dregs of the coffee and everybody's caffeinated and ready to go for the last couple talks of this very engaging afternoon. So our next speaker is Dr. Joe Weiner. He, like Dr. Adeli, is a rec scholar, so came through the research education component of the ADRC. That comes with a reasonable chunk of change to do some research on novel, exciting, innovative projects. And Dr. Weiner certainly meets those criteria. He's going to talk to us all about sleep. He did his PhD at a public university a little north of here, Berkeley, in a really great neuroscience program, and has been a huge, I think, force of good and innovation in our ADRC. So Dr. Weiner, please come tell us about sleep and the aging brain.
Hi, thanks very much. Okay, so we'll just get started. I'm excited to talk to you about maybe a little bit different. I'm going to mix some biomarkers in, but also talking about why we, different lifestyle factors, things like sleep and exercise, we know are really important for staying healthy, but why we care about sleep in particular, why it matters for a lot of the other things we've heard about today. So to get started, so how does sleep actually change as we get older? So this is a study across the lifespan of more than 1 million people in North America and Europe, where they looked at just the hours of sleep people said that they got. Then you see age on the bottom. And you can see, so this is just showing, so the red line is the lowest group, and the blue line is the highest sleeping group. But you can see that as we go into adulthood, it's where the biggest changes happen. So we know, many of you probably know, as kids sleep a lot, but as we get older, things actually flatten out a bit. So there's a lot of variability, but it's not really the case that we necessarily sleep less as we get older. So it's this variability that we care about. But when we talk about sleep quality, rather than the time we spend sleeping, so this shows the same age, the same people, but this time it's the percent time in bed that people actually spend asleep. So what does change as we get older is that people are more likely to wake up, have trouble falling back asleep, so more time waking up and tossing and turning in bed. And this is probably the biggest thing that we're trying to measure when we think about sleep in older people. And why does sleep matter? I think this is kind of a question that all of us can answer. We all sleep every night, hopefully. We know intuitively that sleep really matters for our mood. It also matters for our memory and cognition. So we know this both from our everyday lives and from lots of research studies across the lifespan. But what I'm really interested in is how sleep really matters for brain health. To just give you one example of how we think sleep matters, in particular for Alzheimer's and neurodegenerative disease, this is an amazing study they did at Washington University in St. Louis, where people actually had a lumbar puncture that stayed in their spine for almost 24 hours. So here I think it's showing 12 hours. Yeah, so this was an amazing group of volunteers. Anybody in the room who's had a lumbar puncture can attest. But basically what they did in these volunteers was they measured their tau every couple of hours. And if that doesn't sound bad enough, they actually sleep deprived half of the people. And so they looked at how tau actually changed in the CSF and the people who had a normal night of sleep and people who stayed awake all night. And so the red dots, you can see that the amount of tau circulating in their CSF actually continued to increase the longer that they were awake. And so these were all cognitively normal people. I think they were actually in their 40s and 50s. So none of these people had Alzheimer's disease, but this is some of the evidence that tells us that sleep seems to matter for what happens short term and possibly long term in the way these proteins clump up in the brain. So when we're studying sleep, we're thinking about these biomarkers, these pathologies in the brain that you've been hearing about all day. So amyloid and tau and Alzheimer's disease, Lewy bodies, Parkinson's, dementia with Lewy bodies. And we really think that there's a cycle, we call this a vicious cycle linking these things. And we know this both from these large scale epidemiology studies where people who report sleeping problems midlife, later life are more likely to be at risk for dementia and having these proteins in their brains. But also in mouse studies where if you sleep deprive an animal model of one of these diseases, the pathology accumulates faster. And if you study one of the animals that has the pathology, they typically have disrupted sleep. So you've probably also heard a lot about how we think that sleep is important for cleaning these proteins out of the brain. And so we think that if you think about sleep in a positive way rather than something to be afraid of, you can enjoy your sleep knowing that's also helping to keep you healthy. Okay, so how do we actually study sleep at Stanford? So a lot of you, hopefully, have seen this device before. It's ended up in your mailbox or put on your wrist here in a research visit. So this is, we call an actigraph. It's a little puck inside a rubber wristband. And so I'd like to show you what we actually do with this data, because I think a lot of you have been asked to wear one of these before. We've been handing these out to people for the last 3 or so years and asking people to wear them for 2 weeks. And so the data, we download it, looks like this. So this is what the data is actually, it's actually just an accelerometer. So it's very similar to what you have in your phone or what would be in like a Fitbit or an Apple Watch. But the benefit to these is that it doesn't have a screen, so there's nothing there to bother you. And also it has a very long battery life, so we don't have to ask you to recharge it. It's recording up to a whole month. And so we're able to see people's activity. This is showing 3 days. And when we clean it up, make it look pretty, this is showing one person's 2-week recording, where the white line shows their average activity over the whole period, and the blue lines show each individual day. So you can see very nicely how, you can see when they're inactive, when they're active, and you can see how much variability there is across days. These are all things we're interested in measuring. And so we've been very happy to be able to collect a lot of this data from all volunteers in this study. And now we have over 200 recordings, which has been really exciting to see. So this is looking at across all of the people who are cognitively unimpaired in the ADRC study. And so we're looking at the average activity across 24 hours here. So these little blue dots represents actually 30 seconds of activity. And you can see what is kind of a typical pattern, which is a flat period at night and a very active burst in the morning, kind of tapers off, maybe taking a nap around now, and tapering off into the afternoon, but also some variability. And when we look at people who have cognitive impairment due to Alzheimer's disease, we see a bit more of a bump in the evening, suggested some more sleep disruption or variability in sleep. and also less activity, more of a dip, suggesting people might be more likely to nap. And then finally, we look at people with Lewy body disease, meaning Parkinson's and dementia with Lewy bodies. We see lower activity pattern, which we think is probably a combination of sleep and circadian disruption, but also the rigidity and movement problems that we expect to observe in patients with Parkinson's. So this is just a great way, I think, of visualizing this and the richness of these data. So just kind of an example, we see that in our overall, 200 people wake up on average at 6:30, go to bed at 11:05. It's a pretty good schedule for any individual. And we can focus in on the sleep period, which is my favorite time of day to focus on, and use some different algorithms to calculate exactly how people are sleeping at night. So here I'm just going to be showing across these 3 different groups how much sleep everyone gets on average in individuals. So you can see on the y-axis there, but in general, there's actually not a big difference in sleep duration between people who are unimpaired and people who are impaired. So you can see a lot of variability, even just within cognitively healthy people. But the average for each is about 7 hours, which is, is the recommendation more or less across adulthood. But then when we look at sleep quality, so similar to the plots I showed you at the very beginning, we see that there is a difference. So the average time spent asleep versus in bed as a percentage, it's about 90% for cognitively unimpaired people, but then this decreases in people who are cognitively unimpaired, whether that's Alzheimer's disease or even lower for Lewy body disease. And this is what we expect to see because we know that sleep impairment and complaint of sleep problems are one of the first symptoms in neurodegenerative disease. And it's these circuits that regulate sleep and the circuits that keep us awake that can be affected very, very early on. So some of the more interesting questions I think we're able to explore because of the richness of our data at the ADRC. I just wanted to give you one example. So a lot of you have probably come in for PET scans, which, as some of the other talks mentioned, focus on both tau and amyloid. So I'm going to be showing you a little data with tau PET. So this is just an image of the PET scanner to remind you that what PET is doing is giving us the ability to look at specific molecules or proteins in the brain. And so I'm showing you here someone who has low tau on the top. You can see the brain is very blue and purple, and all the hot signal is really just coming from the skull and areas surrounding the brain. Whereas the person on the bottom this is a person with Alzheimer's disease who has a lot of red in the temporal lobes and going into the back posterior of the brain. This is kind of classic tau signal. So we're able to look at how the amount of tau in the brain is related to how much someone is sleeping and the quality of their sleep, rather than just looking at these categories of clinical diagnosis. And what we find is actually a pretty decently strong relationship. So here the blue dots are unimpaired and healthy controls, and the red dots are people who are cognitively impaired due to Alzheimer's. As you expect, the people with Alzheimer's disease typically have more tau. And what we find is that people's 24-hour schedules are more fragmented the more tau they have in the medial temporal lobe. So people are more likely to fall asleep during the day and wake up at night. And we look just at the nighttime, we see the same pattern. So sleep efficiency that measure, again, time spent in bed, going down the more tau is present in people's brains. So this is just one example of how we're able to combine the sleep data we're collecting with other types of data. And so certainly the kind of plasma and spinal fluid markers that you've heard about and we'll hear more about, we're exploring how these relate to sleep as well. And ultimately, really interested in the question of what drives our sleep patterns, because obviously I've talked to you about how we think neurodegeneration is a major factor, but other things that change in aging also play a role in our sleep. And so these might be different depending on someone's lifestyle situation. We know things like mental health, physical health, like chronic pain can really affect how someone's sleeping. There's also just people have different personal preferences that might drive how late they stay up and how early they wake up. And also, if someone's living in assisted living or has extra care, they might not get to choose what kind of schedule they have. So by measuring sleep in real life, we can get at some of these factors as well as the more neuroscience factors that we're interested in as well. So thank you all for participating in this study, and hopefully we'll have more exciting results to come.
Thank you.
Forgot to mention while we're waiting for our first question that Joe won a really remarkably challenging competition for a grant from the Gates Ventures and the National Alzheimer's Coordinating Center. I should have mentioned too, Dr. Adeli was a finalist in this. So we had two finalists, one winner in this nationwide competition for kind of innovative, I guess, was it digital biomarkers specifically? Yeah. So two finalists, one winner, and really remarkable, especially from these junior colleagues.
Thanks. Yeah, I didn't mention it, but we're really excited about this because basically they decided that we've done such a great job collecting these data, and we, have these promising findings that we're going to expand this to other sites across the country to collect the same kind of data. So we've been able to learn a lot more, outside the Bay Area and see across the country how sleep can change with these markers.
Joe, we have an online question. So I just asked the guests to unmute. Are you able to unmute?
This is
speak?
required, yes.
Thank you so much. Go ahead.
Well, I just wanted to make the observation that I'm in the study. I am very fortunate in that I'm 76 years old. I continue to sleep like a baby. I fall asleep within 2 or 3 minutes of putting my head down in the evening, and typically at night rather, and typically sleep for 7.5, 8, sometimes 8.5 hours. And if I wake up in the middle of the night, I probably fall back to sleep within a minute or two. So does this have any correlation with the possibility of me having Alzheimer's?
Well, it's hard to say on a case-by-case basis, but I think that's a great thing that you are sleeping so well. And yeah, I mean, I don't want to say that it's a myth that our sleep gets worse as we get older. Certainly that is the experience of a lot of people, but it's certainly not the case for everyone, like as you described. Some people continue to sleep well across their whole life. Some people actually say they sleep better as they retire and as they have less maybe societal stresses in their life. So it certainly could only be a good thing, I think, in terms of your risk. As long as you're feeling well rested when you.
Thank you.
Yeah, I can go ahead and go first. So we have two questions here that are pretty related. So first, are there any recommended therapies or drugs to induce sleep? And then secondly, is there anything that can be done to lengthen our sleep time?
Those are great questions. Of course, there are many medications out there that are, used to help people fall asleep. Most of those are sedative in nature, and so we typically don't. I'm not a MD, but generally they're not actually promoting the healthy kind of sleep that people fall into naturally. So those aren't always the answer, but talking to a sleep specialist is always a good idea if sleep is something that's causing stress for you. But there are a lot of non-pharmaceutical ways of improving your sleep, including things like cognitive behavioral therapy for insomnia, which has been shown to be more effective than in a long term than some sedative drugs. But I think more and more, there are a lot of supplements making claims out there about helping people sleep, and not very few of them have actually been tried in any kind of trial. So I would always be skeptical of any claims of improving sleep. But as long as something isn't expensive and doesn't have any side effects, if something helps you sleep, it's usually okay to keep taking it, because sleep can be something that changes a lot based on our stress and anxiety. So if you find something that works for you, it's usually a good thing.
All right, thank you. So they're in kind of relation to speaking about medications. How does using sleeping pills like Ambien or Valium affect diseases such as Alzheimer's disease?
Yeah, so I don't think that there have been, so there are some studies that have shown that people who take those more sedative type medications like Ambien actually are at higher risk long term of progressing to dementia. But those are hard to say because people who turn to those drugs may already have concerns that they're addressing by taking those drugs. So I don't think that there's very conclusive evidence that says that they put you at higher risk. But we do think that those sedative drugs can make people feel worse the next morning. Many people have that experience. So, and if someone is having trouble with the memory and cognition, usually taking like a heavy sedative is not the way to go. But talking to, a sleep specialist is the best thing.
Great. I have a question regarding your activity profiles. The 24-hour activity profile showed lower activity. Question asks, did you find high activity levels at night during sleep in those with DLB?
Oh, that's a great question. So this might be, I'm not sure if this person is asking about REM behavior disorder. Yes, you are? Okay. Thank you. Okay, so this is actually a really interesting point and something that we've observed in our data. So REM behavior disorder, maybe I should take even a step back. So in REM sleep, which we spend about 20% of the night in, there is a signal from our brainstem that actually paralyzes our muscles. And this is essentially thought to be so that we don't act out our dreams, because our brain is, the activity in our brain looks very similar to wake while we're in REM sleep. So by paralyzing our muscles, we don't act out our dreams, we stay still in bed. So people with REM sleep behavior disorder have degeneration of this circuit, and they begin to act out their dreams. And so there's a question of if someone who had this disorder was wearing a watch, would we detect that? And actually we do, and we've shown with a collaborator who was previously at the Stanford Sleep Clinic, Emmanuel During. He gave the same watches to a group of participants with REM sleep behavior disorder, without dementia with Lewy bodies, without Parkinson's disease, but it's expected those people will eventually progress to have Lewy body disease. And he found that you could actually use the watch to detect that they had REM sleep behavior disorder pretty well. And so in the group of people at the ADRC who have Lewy body disease and Parkinson's disease, we do expect that some percentage will have REM sleep behavior disorder. And so we actually see in the nighttime activity, there's this sort of two distributions. So there are people who have it, and people who have REM behavior disorder show more activity at night than we would expect. And people who don't have it actually show less activity at night than we'd expect, which we think is due to the rigidity that we see typically in Parkinson's, which is both during the day and at night. So I think that this potentially one kind of exciting, like very obvious biomarker that could be developed from actigraphy software measurement is detecting REM behavior disorder potentially earlier than someone might be aware of it themselves.
Okay, I have a couple of questions, then I'm going to merge into one. So, how is sleep efficiency or quality defined both in general, with the Oura Ring, Apple Watch, etc., and in your studies? And can we rely on these things like the Apple Watch or the Oura Ring to credible and to accurately track our sleep quality?
Yeah, that's a really great question. We get this question a lot, and we're trying to understand how these we'll call them consumer devices relate to the kind of things that we measure in research, and we're actually hoping to start using some of them in our studies soon. So the device that we're using is only measuring acceleration, so just movement, whereas the Apple Watch and the Oura Ring, Fitbit, and some other devices measure heart rate as well. And with that heart rate information, they can measure what sleep stage you're in, because we know basically your heart rate variability changes as you go from deep slow wave sleep, non-REM sleep, into REM sleep. So they give you a little bit more information. But these devices, they are kind of a black box because they are proprietary software. Sometimes they clean things up a little nicer than just what we would pick up with the raw data. So we're a little bit skeptical about using them for research for that reason. And a lot of them have also been tuned up to work well in healthy young people, probably people who exercise a lot and are tracking their daily behaviors. It's not always clear to us that they are picking up the same kind of things we would care about for someone who's older and who might be concerned about their sleep quality. So I would approach them with caution, but but I think they can still be a helpful tool if you're interested in, learning more about your own health. Oh, I don't have to.
Okay. It looks like tau in the cortex and also in the lower brain or the hippocampus. Is that related to dream or REM processing?
We don't think so. We don't have evidence that tau relates to REM sleep. REM sleep is actually regulated more in the brain stem, but I can, if this person finds me afterward, I can tell you more about other studies we have on that. I've been asked to shorten my responses.
Okay. Okay, and then another quick one. I heard that the lymphatic clearance from the brain is more efficient if sleeping on the right side. Is that true?
That's really interesting. I'm not sure where you heard that, but there's been one study. So the lymphatic system is thought to be the system that clears amyloid and tau and waste products from the brain. And it's thought to be more active during sleep, although this has really only been shown conclusively in mice at this point. And so there was also one study showing that posture was important for lymphatic clearance, but this was again in mice. And I am not an expert on mouse physiology, so I can't say how their posture translates to ours. But so this remains an area of speculation. I wouldn't be concerned that one sleeping position over another. Although I would say I've been approached by one person at NASA about the lymphatic system with concerns that it might not work well in cases of no gravity. But hopefully nobody here has to deal with that problem.
Gonna say I don't think Joe has seen a sort of what was it, 11:30 to 6:30 a.m. sleep night in a while because he has a couple young kids. I don't know, so that's like a dream. He's moving towards that one day. It gets better, I promise. All right, so our last scientific talk of the afternoon, we're going to hear from our community advisory board as well, but the last scientific talk will be from Dr. Ted Wilson. So Ted's an instructor now in the Department of Neurology, and without sort of exaggerating, Ted is really the machine that keeps our biomarker work running. So Ted has worked very hard, really tirelessly, to get this up and running over the last 5 years, or more, to the point now where it's automated. We get it in everybody. It's very reliable. And in addition to leading that entire effort, Ted's also making hay with the data itself, and I think we'll hear maybe a little bit about both today. So, Ted.
So thank you very much. While this is getting set up, I'll have to say I had nothing to do with Joe rushing his responses. I love listening to Joe's answers. So I'm really happy to be here sort of as a junior person, to be invited by the organizers. We don't often have the opportunity to meet you folks. And so this is sort of an act of demonstrating our appreciation. To us, you're known as, 9-digit anonymized numbers. So it's nice to actually see some faces with those numbers. So I'm going to talk a little bit about the blood biomarkers that we've been working on and what sort of your data and your participation and the blood that you have given has allowed us to develop. And we're always interested in the biomarker core to sort of develop new biomarkers that can give us greater insight into the processes underlying aging and Alzheimer's disease. And so starting off very, very generally, what happens to your blood samples? You come in and you go through the blood draw and they're carted away. Well, we use them basically, as Mike mentioned, we look at markers that can tell us about the stage of Alzheimer's disease, the staging that takes place. And that's sort of our core workflow. We do that with all of the blood samples and the CSF samples that are coming in. But also importantly, we use them to develop new markers that can help us to detect early Alzheimer's disease. And I'll show more on this in just a moment, walking you through one example. Beyond that, at Stanford, we're really lucky. We have so many collaborators who have so much worldwide expertise. There are folks who study these biomarkers and they actually use them to tell us something about the biology underlying the disease. So it's not just a data point or a result or a concentration. All of that goes together and is combined with the data that we have. And then these samples are stored in special ultra low temperature freezers. So these freezers are kept at -80 degrees Celsius, and the samples are stored for future studies. So we have been using samples going back to 2015, going back to 2011, including all the more recent samples that have been brought. So in case you're interested, this is one of the instruments that we're very fortunate to have at Stanford. I'll go back a slide. So this is from the catalog, the glamour shot of the instrument. It's called a LumiPulse instrument. It's a fully automated system. Our tests are stored on board the instrument. We take the blood that you have donated and we load it on the system, and the machine has everything on board. It has a little fridge on board to keep the tests, and in a half hour, we get the concentration and the readout. And this is a picture of the instrument in the lab with the research assistant, Michelle, for scale. This is what it looks like, and Michelle has worked with us very tirelessly in generating a lot of the data. And so Carla has shown this previously, an example of this slide. And what's exciting is that there are detectable signs of Alzheimer's disease in the blood. It's much more accessible now. And these are the core characteristics of Alzheimer's disease that we've been talking about all day. So we have amyloid, amyloid beta 42 and amyloid beta 40 that can be detected and measured in CSF and in plasma, or through PET scans, so we can detect amyloid beta fibrils. We also have tau fibrils, which can be detected by PET, and we can look at phospho-tau and total tau in cerebral spinal fluid and plasma. I won't get into the other biomarkers, but we do have a few that we're developing for astrocytes, so biomarkers of inflammation, biomarkers of the blood-brain barrier, them as well, and also neuronal biomarkers that relate to different aspects of neuronal health. So we can assess these all together. So what's nice about this, with the amyloid beta pathology, we can detect it using amyloid PET, we can detect it using a CSF sample, and we can also detect it using a plasma sample. And the blood samples are much more preferred for us because we can repeat them more frequently, they are much cheaper, and they're much easier to give. And we can get literally very large volumes of material. And so in the last year or so, we've measured plasma amyloid beta 42 and amyloid beta 40 in the plasma to see how well will this work as a biomarker for Alzheimer's disease. Can it stand in for amyloid PET, and can it stand in for CSF? And so here are the results that we have. So what I'm showing here on the graph is the plasma amyloid beta 42/40. And in this case, as amyloid builds up in the brain, it actually decreases in concentrations outside of the brain. So the CSF levels go down and the plasma levels go down as well. And in the brain, the PET levels, the amyloid PET levels, those increase. And so what we can see is if we look across different participants, so clinically unimpaired, mild cognitive impairments, and Alzheimer's disease, we do see a decrease in the levels of plasma amyloid. And this kind of comes back to what Mike mentioned earlier at the beginning of the day. We separate these folks based on amyloid positivity defined by a different metric, either CSF or PET. And we see that this change in plasma amyloid beta is really apparent. It's really obvious in folks who are amyloid positive by another measure. So this is showing us that it's actually working quite well. So if we remove the clinical diagnosis then and just group people together by their biomarker status, so their amyloid A or tau status T, we can see that folks who are amyloid negative and tau negative have a bit of a range. But if you're amyloid positive or amyloid and tau positive, we do see that decrease. And then one of the most well-studied and the largest sort of genetic risk factor for Alzheimer's disease, carrying the ApoE4 allele. And what's really interesting about this blood-based biomarker is we actually see it reflected in the concentrations, regardless of your clinical status. So if you're clinically unimpaired and carrying 0, 1, 2, or 1 or 2 copies of the ApoE4 allele, we actually see that reflected in the amyloid, the plasma amyloid levels. So this is really exciting. It's telling us that this is probably a very positive biomarker in blood. And so biomarker is great, it's fantastic, but how does it relate to memory? And so here we're showing memory performance on a collection of cognitive tests. And so a lower score is indicating worse performance. And what we see is we separated individuals who are clinically unimpaired, cognitively unimpaired, and those who are cognitively impaired, so with a diagnosis of Alzheimer's disease or mild cognitive impairment. And we do see a correlation with the levels of plasma amyloid when there is a clinical impairment present. Right? And that's really important as we, as a field, address what do these biomarkers mean for people if they're not already impaired. And so don't sell the boat, don't retire, don't make all these big life changes because a biomarker diagnosis alone is one piece of evidence, but it's not the be all and end all. And I think you have to have conversations with clinicians. And so we're really excited about this. We asked, well, how well do these accessible blood biomarkers relate or correlate to other measures? So we have here on the y-axis, CSF amyloid beta 42, and we have plasma amyloid beta 42/40 ratio on the x-axis, so blood versus CSF. And what we can see, if you squint and look overall, there's a pretty good association. They're correlated pretty well. And we have shown here are the cutoffs that we use to define abnormality. And the arrows indicate abnormal again. So, and CSF, a lower number suggests abnormality, plasma, the same thing. So what you can see is that generally, as plasma amyloid beta 42/40 ratio is high, it's also high in the CSF. And if it's low, it's also low in the CSF. So we can look at these cutoffs now, and they're shown on both lines. We get 4 quadrants. So essentially what we're looking at are people who are amyloid positive by PET, or sorry, CSF, and amyloid positive by blood. They're concordant. At the bottom left, we see folks who are positive by amyloid beta 42/40 in blood and positive also in CSF. What you can see in the two, the upper left and the lower right, is there's a really interesting where folks are positive by CSF, but not yet by plasma. So we're wondering, is this telling us that plasma is actually changing first, that we're detecting this abnormality first in the plasma? And to sort of get a little more information on that, it's also true when we look at blood amyloid versus amyloid PET. So again, we have a large population of folks who are positive through blood, but are negative by PET. And so what we did to dig a little bit further into this was to take out those groups. So the folks who were plasma positive or plasma negative, but PET and CSF negative, and check to see, did they show differences? And the differences we were interested in are they related to future Alzheimer's disease. So we see in terms of longitudinal performance on cognition. So over time, we can look at the slopes, so the years since baseline on the x-axis. And the folks who are plasma and CSF negative, they don't really show much change, no negative slope. But the folks who were plasma positive but CSF negative, they actually show a significant, although slight, level of decline. So this suggests they may be on their way to on Alzheimer's disease in the future. We also, Joe mentioned tau measured in the entorhinal cortex as a marker of early Alzheimer's disease pathology, and we do see that the folks who are plasma positive first show higher levels of entorhinal cortex tau. And so I'll show a little bit more data looking at the future cognitive decline just across all of the cohorts. So again, we have trajectories on the MoCA or on the memory composite over a 6-year period. And what we can see is that folks who are diagnosed with clinical impairments who are positive by amyloid beta in the blood show a significant decline over time. That's predictable, but not so significant in folks who are clinically unimpaired. And this is true for both metrics. So again, it really highlights the fact that you really need that clinical diagnosis in part to really understand what your effect of amyloid positivity will be on cognition. And so with that, I'll go through the summary of the findings. So we now understand that plasma A beta 4240 declines early in the development of Alzheimer's disease. And it correlates nicely with other measures of amyloid pathology, including CSF and PET. It allows us to monitor Alzheimer's disease changes over time. And we're also hoping that it'll be useful in monitoring disease-modifying therapies as well. So with that, just like to mention that none of these findings would have been possible without your participation. So thank you very much. I guess I should thank as well. This work was led by another instructor in the neurology department, Ali Trell, who's fantastic, with Christina Young and Beth Marmino helping. And this is our small biomarker team who's helping put the work together. So I'd be happy to take any questions.
Lisa, you want to lead that first question?
Sure. So the first question that we are getting is, what about tau relationships to the measures you've been looking at versus amyloid?
Yeah, that's a really great question. We do see significant association between amyloid levels as measured in the blood with tau PET as well. What's really interesting is we're considering trying to match the different timeframes of both of these pathologies. And so this amyloid change that happens, and I think you may have seen it when you looked at the data, is that there's a real floor effect. And the levels drop and they pretty well stay low, even though you're progressing through different cognitive stages. And so in order to have that correlate with tau, which is very tightly tied to cognition and disease staging, it's a little more challenging because they're sort of on two different timeframes. But what we do is we look at the earliest development of tau and that appearance, and that's sort of been very well studied by other groups, and we know where to expect it in the brain and at what time point. And so we do see very high levels of tau early, correlating with amyloid beta in the blood at the early time stages.
By how many years on average does decline in 42/40 ratio precede clinical symptoms?
That's a really, really, really great question. And so, what we can do is there are cohorts where in 300 or so families around the world, Alzheimer's disease is an early onset at genetic form. And in those cases, we actually can predict very accurately the age of onset of the Alzheimer's disease. And in most other cases, 95% of Alzheimer's cases, those are sporadic and they can vary quite a bit. But in using these early onset forms of Alzheimer's disease, we're able to come up with those time points of those changes. And their data shows that these levels change and become significant 15 years before the onset of clinical symptoms. So again, the human brain has an incredible capacity to compensate. As I'm standing here, I have maybe 35 words that I could replace the word agitation with if I'm not able to draw it or connect to it. So I can compensate, and I can actually deal with quite a large amount of neuropathology before it becomes apparent. So in one sense, it is important that we have these biomarkers because they can tell us what's happening underlying these conditions. But it's also important to know that they have to be sort of integrated with what the clinical neurologists and neuropsychologists are telling us.
Okay, regarding the new blood marker, A beta 42/40, do you test all the participants for this? And would Stanford consider sharing the results with the participants?
Yeah, that's a really, really great question. So, the first blood biomarkers that came out, and maybe some folks here maybe have ordered them or have had experience with their clinicians getting access to them. Those were the p-tau antibodies. And we're showing data here from amyloid beta, which is thought to be working pretty well. And there are other sets. So I think what's really, really important is actually to integrate all of those biomarkers together because they all tell us a different piece of the story. In order to get a full view of what's happening, it's important to access as many as you can. And so we measure them on all of the Stanford ADRC participants, and we measure them year after year. And I think there are discussions with the ADRC leadership and the Give Back Committee on how to go about returning that information back to participants responsibly, because everybody has a right to their medical information, but at the moment it's not quite actionable. So what do you do with that information? And so in some cases you could have a positive test and it may lead nowhere. You may not change cognitively, or it may be predicting an early onset or an earlier onset of Alzheimer's disease. So it's really difficult to understand right now how those may work. So we do have to give that data back responsibly. And that's sort of, I think, the plan of the committee.
Do you foresee using the early predictors leading to prophylactic early treatment?
I think so. That's, right now, the goal and the biggest benefit has actually been, as Mike mentioned this morning, in pre-screening and making sure the right folks are getting into the right trials at the right time. And that has been crucial in having positive trials so far and in serving as outcome measures for other trials that are ongoing. But the drugs that are currently available right now, or the new ones that have been recently approved, are associated with a lot of risk and side effects. And so the question is, would that be true if it was initiated 10 years earlier? And that's not well known. There are trials that are working on sort of the prophylactic aspects of the drugs. But I think ultimately that's where we'll end up when we have a combination of drugs and somebody who is perfectly defined by biomarkers. They'll be able to begin trials or begin treatment much earlier. Yep.
What are your thoughts about the many blood biomarker tests like Proclivity2? Do you expect a lot more to be approved by the FDA in 2025? And do you have a preference?
Yeah, no, I definitely have preferences. The important thing is that the direct-to-consumer tests might not be reliable. So I'd always suggest that folks do, if they're willing to, if they're wanting to get this data, to do so under the supervision of a clinician, because there are horrible tests that are out there and they're not very well validated. There are tests that are undergoing review now by the FDA, and those are scrutinized much higher, and their performance has to be much higher. So I think that's really important. There are probably 4 or 5 other tests that are about to be approved by the FDA in the first quarter of next year, which work pretty well. And some of the tests that we work on in the ADRC here, the same instrument, that will be one of them. But I think that's the most important thing is, use something that the clinician trusts, because they're the one. Oh, the power of the assay, maybe the shortcomings of the assay.
Could future studies lead to blood therapy for the treatment of Alzheimer's disease?
I'm going to pass on that one because I don't quite understand. Yeah.
Okay. And then what is considered early onset Alzheimer's?
Right. So in the genetic forms, roughly speaking, we would discuss 65 years of age and younger. We would generally sort of accept as an early onset form. But for those genetic tests or those genetic forms, we do recommend working with a genetic counselor, and depending on sort of which SNP or genetic difference that someone's carrying, the age of onset could vary. So it could be as young as 35 or 45, 50, 55, 60 in those ages. But roughly, broadly speaking, we think that younger than 65 is an early onset form. Thank you.
Sorry, there was one more. I'm going to see if I can try to translate this. So I believe the question is basically, given the blood plasma biomarkers, are genetic markers also being found in terms of any of these diseases? I believe that's the question online.
Okay. Very interesting. I mean, so when we say the word biomarker, they can cross across many domains. So we have imaging biomarkers that we discussed.
Sorry, blood plasma.
Yep. And so for the blood biomarkers as well, one of the things that is nice, we have access to at the Stanford ADRC, and this is through Mike's work, is we're able to extract DNA from the blood sample that's given, and we're able to do whole genome sequencing in that case. And that allows us to look for the gene variants that are already known and identified, or as Mike has published, locating and identifying new risk factors and new genes that are present. So yep, they can go together.
Thank you.
Thank you.
So I'll take the lead in introducing our last series of speakers. I've had the good fortune of working with our community advisory board members over the past couple of years, along with the outreach, recruitment, and engagement core. And Wei Ting is here representing our core. So thank you also for being here, Wei Ting. We will have Leslie Dubridge coming up to join us, as well as Benjamin Yen coming up to join us. And online, we have Lupe Morales. So Lupe, I'm hoping that one of these monitors will show you when it's your turn to present. It's going to be an interesting technological question. So I believe, who's going first? I believe Leslie's going first. So I'm going to let her introduce herself and share with you a little bit about herself.
Thank you, Nushka. Good afternoon, everyone. Thank you. As Nushka said, I'm Leslie Dubridge, and I had the pleasure and honor to be part of the founding group of CAB members. We started with 8, and now we're at 12. And my background is I work for a local city government, but I also am a coach under the Be Well program. I'm a national board certified health and wellness coach, teach fitness classes to seniors, functional fitness, and just an overall senior advocate. And I am just really interested in this particular disease. It doesn't run in my family. However, I have many friends that have been affected by it. And so it is with honor that I serve on the board. There was a quote that I've heard before, I think it's apropos to kind of sum up who CAB is, and that is: service is the rent we pay for being. If it is the very purpose of life and not something that you do in your spare time. And that's what I've found serving with others on this board. Let's just talk a little bit about the actual aims of the board. So do you have the first slide? Okay. Oh, there it is. Forward here. Great. So there are 5 aims. And I just wanted to go over them really briefly, but they're very important. As you see, the first one is to provide guidance to the Stanford ADRC on priorities related to Alzheimer's disease services, education, and research. And how that can show up is by way of such as memory screenings and sharing of learned best practices from other similar programs throughout the country. So people contribute a lot at our meetings. The second one aim is to provide guidance on development of community partnerships. And that's really key. And research outreach opportunities for the Stanford ADRC. And that shows up like some of you might have attended the recent Walk to End Alzheimer's. So they're tabling events at events like that. The third aim is to provide guidance on successful recruitment strategies to increase participation of underrepresented communities in ADRC research projects. And that would include right now, the major priority would be, the groups would be Asian populations as well as Latina. However, every ethnicity is open. I'm sorry, let me go back. Every ethnicity is welcome to be a part of this board, this program. And the fourth one is cultural centeredness. That is talking about the feedback on accessibility and cultural centeredness. And what that means exactly is talking about journey review, which we're going to hear from Lupe later, and then also accessibility. So those are the aims, and we as board members are here to support everything that ADRC in that way, and whatever we can contribute, hopefully is helpful to them. There are a lot of ideas that float around at these meetings. It's very vibrant meetings, and I love that one of the researchers also attends, Dr. Henderson, and so me not being a science background person, I learned so much. This is just incredible. Then we serve as ambassadors to the community. And just like me, I'm just a senior advocate, health and wellness coach out there, each one reach one. So we're very grateful for that. And then who are the boards? There's some that are here and some on Zoom and some that couldn't be here today. But I do want to acknowledge you're going to hear from one of them that's also here following me, two of them following me. But Benjamin Yen, he is a caregiver. He is on the board. Denise Coley, she's a Parkinson's disease patient and advocate. Elisa Wilkerson is here. Would you raise your hand or stand up where you are, Elisa? There she is right back there. Thank you for being here, Elisa. And then we have Christina Lugo. She's with Avanatas and president and CDO of that. Jaime, he joined recently, Gutierrez. He's a study participant. Are you here, Jaime? Oh, there you are. Okay, great. Raise your hand. Thank you so much. And then yours truly, Lupe Morales is going to be on following me. She's a patient advocate and research participant. So you see, we have a cross mix of so many different people. Sandra Green, she's with the Alzheimer's Association and the Northern California chapter. So she brings a lot also to the board. Sandra Winters, she works not far from where I work. I work for a local city government, wonderful woman, senior co-siders. She's the executive director. And then Sarah Langer, she's a Stanford ADRC patient. Scott Roney, he's a veteran. He joined probably late last year. It's great to have his contribution. And then Ting Peng, he's a patient and research participant advocate. So it was formed in January 2023. As I said, I was very blessed to be part of the founding group of 8. And now there are about 12 or 13 that are on the board. We have quarterly meetings that last for about 90 minutes. And we've had 8 meetings to date and between 2023 and 2024. Now, some of you may be saying, well, that is great. How can I be a part of the board? So Wei Ting have some sign-up sheets in the back. So if you're interested at all, please see her and sign up to learn a little bit more about serving on the board. I'm very grateful to Nushka, Wei Ting, Lisa Goldman, and also Dr. Patricia. They are guiding us and they're helping us to understand more about what they do so we can know how to better serve them. So real excited. So thank you for hearing a little bit of the backdrop of where we were. And now I'd like to introduce Lupe Morales, who's going to speak a little bit about the patient journey. And let's see if she gets up here. Ah, there she is. Yes.
Hi there. I can't see you, but I imagine you can see me, so I don't get nervous.
We can see you.
Awesome. Wonderful. And can you hear me okay?
Yes.
Wonderful. Okay, so my name is Lupe Morales. I'm a native of Los Angeles. I got into this whole research participation in Alzheimer's world because of my mom, Josie Morales, who was diagnosed in 2019. I have been part of this particular CAB since January of 2024, but I sit on others. I'm also a research participant. And so I sit on from research participant advisory boards to community advisory boards, mostly in Los Angeles or in California proper. And I am a care partner for my mom, Josie, again, a research participant, an organization development practitioner turned aging and brain advocate. So I'm very happy to be here and a part of Stanford University ADRC's CAB, very much so. And in participating in other types of advisory board, I have to say, and want to express my thanks, and also that it's very unique to have these researchers not to work in tandem with us on the community advisory board. And what I'm most impressed with, and this does not happen, is that a neurologist, MD, professional, very busy person, along with the other researchers, Dr. Victor Henderson, shows up to our meetings, lets us know when he's going to be late. Or if he can't show up for the whole meeting, he's at the end. And he just listens and asks questions. And it's a bi-directional learning experience. So I wanted to let you know that that is unique among the CABs I sit on, is to have that type of interaction and interest. And I see it, I get it, and I love it. So with that said, I wanted to highlight some of this CAB's projects, or one of the main projects, which is the participant review journey. And in this participant review journey, the goal or the aim of this was to streamline and simplify consent and post-consent processes for the Healthy Brain Aging Study. And you all, most of you of our participants out there, you know the consent form, how it is. It can be improved, and that's what we were engaged to do. So really the goal was, and our goal, one of our main things is to improve the research participant, or the study participant experience. And so what we did with that is, or how did we do it, you might ask. We actually had 4 meetings to look at the consent form, each lasting about 90 minutes. And there was prep time to digest some of the information before we gave feedback. And altogether, it was 4 meetings, each meeting about 2.5 hours with prep, etc. And the first meeting we had about the consent form was really with all the CAB. As Leslie mentioned, we have 12. And so all 12 of us kind of got a briefing of it and what was needed. And then what was asked of us is that volunteers, a few of them, 4 or 5, to volunteer and to have these deeper meetings where we would go through page by page of this consent form. And altogether, the consent form was 28 pages of content. So again, what I love about this team that is working in collaboration with us is that they broke it down so that we were not overburdened by so much information each time. And they took that into consideration, which I know I appreciated. So during these 4 meetings, every portion or section of the consent form was reviewed and was examined by the 4 members of the CAB. And staff did a great job. And again, the consent form was 28 pages in content. If you could, there we go. And so.
You want us to advance the slide?
I think yes. Actually, you can go to the one previous, I believe. Thank you. Oh, sorry, I covered that. Yes, go to the next one, consent form assessment. So, what did the CAP actually examine here? Well, we examined the language used in the consent form and whether it was clear and easy to understand and accessible to the public and in our communities. The second thing that we examine is the technical terms used. Were they confusing or not? And then try to find different ways to simplify and explain these things. And what was interesting in these discussions is that we actually, we're talking about different examples to use to help with the technical kind of wording and phrases to make it easier and provide those examples. The third piece is reading level, if it was appropriate and if it could be improved. And specifically, the discussions that we had in smaller group was around the language, again, of the consent form, its accessibility, whether the materials for people who spoke English as a second language were easy. And we also raised issues and had a long discussion around literacy levels and literacy challenges of different communities that we were looking at, and different ways to present materials so that that issue would be less of a challenge for either the research participant, their study partner, or their families. And identify potential needs to culturally adapt any part of the process, language and data. Next slide, please. All right. So one of the important outcomes, in addition to giving feedback about the consent form, is actually developing this visual that you see here. And the visual is actually meant for researchers to help describe the process from beginning to end. And it mirrors kind of the consent process or what the research participant might see in the consent process. It was developed, again, as a visual to mirror that process and to just help researchers kind of, again, go from beginning to end and post study with a visual. For me personally, even if I were to use this or share this with a participant, it helps me if I had a language issue or a literacy issue. There are photographs or images that will help me go through that process. A reminder and focus of making research participants, the experience that of study and research participants, easy and stress-free. If they can see it from soup to nuts. And then you see at the bottom where it says things to know, which are highlighted things that, for me personally, when I was a research participant, did not know. And folks on that team failed to tell me for a variety of reasons. But that said, I want to say finally and emphasize that there are different ways for communities and for research participants themselves to participate in ADRD research. For me, being on a CAB and being a CAB member or advisory board member and sharing my experience as well as learning like I did today, continued learning. And for anyone who is a caregiver and who can have access to the internet as well, and whose families are impacted by Alzheimer's like mine, living through my mother's journey, I really do encourage people to think about being a community advisory board or in a research participant advisory board member. It provided not only a way to learn and dialogue with other people who are interested in this, but also a support as a study participant. So that said, I want to hand it over to my colleague, Ben. Ben will talk a little bit about the future and the CAB. Thank you.
Thank you, Lupe.
Thank you, Lupe. Hi, my name is Ben Yan, and I'm representing caregiver, and I work in the high-tech industry and still working full-time at 73. And my wife has an early onset genetic dementia called CADASIL. And so some of the very interesting things that for me is going through with her. This is her 9th year already. So anyway, let's look at the 2025. By the way, I'm the last speaker, so it's in between me and the final remarks. I will try to be very quick. So anyway, on the 2025 plans, the first one we are going to look into is involvement with review and action plans for the return of results. So it's very similar to the what Lupe just going through this participant journey review. So basically, we want to see how we can make this more effective and also efficient process itself, and also get more benefit for the participant as well as for the ADRC program itself. So what we will do is we will have the CAP members' representation in the large effort, as well as doing some presentations from that group to the overall CAP meetings. And the second, let me see, can you forward? Okay. Okay, thank you. So the second portion is really dear to my heart. It's the resources for caregivers. So again, we want to find out more of what's the needs and wants from the caregivers. And as a matter of fact, I would like to also suggest, if you have any suggestions or what you would like to see, please also input it to ADRC. And one of the things I like very quickly comment is some of the things we have seen, or what the Alzheimer's Association taught me very early on, is as a caregiver, we have to be very, very careful, because we can be gone before our caregiving loved ones or partners. So we have to be very careful about that. In the meantime, we need a lot of support. And one of the things, for example, is how to have lighthearted. And the laughter is definitely one curing factors. And sometimes I do have a lot of stress, and you probably can tell. And but I'm very happy also the arrangement today as a greeter. I have an icebreaker with a lot of people come in, so give me a lot of laughters that way too. So anyway, so what we will do is we'll try to find out a little more from what the other ADRCs. By the way, in the US is a total of about 33 ADRCs, I believe, and also from maybe other countries like Japan, Korea, and Taiwan and so forth, which aging population is become much dominant than the younger ones. So that's what we will be going forward. And certainly if you have any suggestions and so forth, please do let us know. And again, thank you for your participation. And I thank you for listening to us.
So if there are questions for the CAB members that have presented, please also, I guess I'll take one right now. What is the relationship between the ADRC and the Healthy Brain Aging Study? You want me to take that?
Please.
They're one and the same. We just call it the Healthy Brain Aging Study because our institutional review board needs a name for the study. So that's what it is. But the Alzheimer's Disease Research Center at Stanford is the same thing. Other questions? All right. And is there a link on Stanford ADRC website for caregiver support? There is a resource link on the website. Boy, I can just answer these myself. And there is a resource link under information for families and participants. You can go, and there are some resources that we've cited on there. Going back to what Benjamin said about, please let the ADRC know if you have any suggestions. I oversee the ADRC Stanford email, as you all probably know by now, because I've been in touch with you through that. So feel free to send suggestions or requests. We'll do our best to accommodate. There are some limitations in terms of what our webmaster can post, etc., but we will do our best to put as many resources there, ideally both in English and other languages. So we'll do our best for that. Is there a way to allow participants to self-organize, create more opportunities to support and learn from each other's journeys? Feel free to write in some suggestions to that effect. I can tell you that early on when we formed the Stanford ADRC, I was involved with the outreach group in holding some workshops for caregiver support. I worked with Dolores Gallagher Thompson in leading some of these workshops. I don't know if you know, I'm also a licensed psychologist and a background in neuro and all that. So we did host some early on, and if we can somehow regroup some resources in the next iteration, if there's a strong need, please let us know. We will see what we can do. I can't promise, but I sure will do my best. And there's one from back there. Go ahead, Lanja.
Yeah, somebody is asking how they can donate their brain and body to research, and who to reach out to.
Nora will, okay, go ahead, Nora.
So we have our lovely coordinator at the Stanford ADRC. Currently, his name is Nicholas, and we can perhaps provide information on how to contact him. He is your point person for all things brain donation related to the Stanford ADRC.
And so the brain donation program, again, on the website, there's also some information about brain donation on our website as well, the ADRC website. If you look on the left column, if you read down, there will be information on brain donation. And we greatly appreciate that, because the more we can learn, hopefully, the quicker we can get to some, hopefully a cure. And so before I hand over the microphone to Mike for closing remarks, I want to personally thank you all again very much for your time, your patience, your understanding throughout this process today. I am so excited that we had so many people come despite inclement weather. And again, first and foremost, I'd like to thank all of you again for coming. Please join me in one final round of applause to all of our wonderful speakers and the wonderful work they've been doing and sharing. And the wonderful staff who have helped put this together today. I couldn't have done it without you. And Jamie, thank you again. A final request is on your agendas, we had a link. It's actually the same link that you signed up on. We would greatly appreciate your feedback and suggestions for other topics and for future Participant Appreciation Day events. Our goal is to continue to do it hybrid, virtual, and in person. So if you have additional topics and things you'd like us to present on, we will do our best. Thank you all again so much, but Mike has some final words.
All right, well, you guys are probably tired of being thanked, but we'll thank you one last time. But before we do that, let's thank Nusha for putting this all together. Really remarkable day. And Jamie and the volunteers, who I think are actual volunteers, not voluntold. So, everybody's here helping out because we believe in effort. So I guess maybe returning to Faulkner's quote about, how do we prevail and not simply endure through these neurodegenerative disorders. The recommendations from Faulkner himself are, we need endurance. And I think that's true. There is still the grit factor, the daily grind of these diseases. So we do need to endure through them. He talks about compassion, which I think we've already seen a lot of here today, and feeling this community, you get a sense that people are helping each other out. Certainly the Community Advisory Board, that's very clear, and we appreciate your help. So compassion. And then he mentioned sacrifice. I would probably change that to generosity. And we've seen, the results of your generosity in these incredible studies today. If you don't think, after a day like today that we can move from endurance to prevailing over these disorders, inspiring, compelling talks from, a group of rising stars in our program. But mostly, again, closing on a note of gratitude for all that you've given us: blood, sweat, tears, spinal fluid, skin biopsies, and brains. We need brains. Everybody loves brains at the end of the day and not before, as I said earlier. All right. And with that, thanks once more, and we'll see you next year. Bye-bye.